Hello everyone and welcome to the video. This is a project presentation for the course Robot Control, and in this video we will talk about our project evaluating region of attraction for dynamical systems. The video lecture will cover the basis of control and control system designs and region of attraction. Further, we will talk about fundamental properties of stability and how it is defined. Then we will dive into Lyapunov stability and how to find its correct Lyapunov candidate. We will study the effect of such system on nonlinear system like inverted pendulum. The second half of this presentation is focused on introducing novel methods to compute region of attraction in nonlinear system by using methods like maximum Lyapunov function, sampling based methods, and by using safe learning in control systems. The control system is broadly classified as linear and nonlinear systems. Linear systems are systems in which input and output are linearly dependent and can be expressed in the form x dot is equal to ax plus bu. These systems can be solved using analytical method by either using Laplace transform or by finding transfer function of the system to get solution. Such systems always have a valid and a global solution, and we can employ a controller like PID or PD for such systems. On the other hand, nonlinear systems are dynamical in nature, in which a function describes the time dependence of a point and are defined by x dot is equal to function of process, where t is the time, x is the state, and u is the input, which are shown here. Such systems cannot be solved using analytical methods by using Laplace transform. Hence, an alternate to this is by using numerical solution, but it is valid for only certain input-output states only. Also, the solution for such system may be exist in periodic time interval or maybe exist in certain conditions or globally or locally valid. They are controlled using controllers like adaptive or robust controller. Since most of the systems in nature are nonlinear, so it is ideal to study nonlinear systems and how to obtain stability for such systems. Further diving into more technical fundamentals of stability. For any control problem, we are given a physical system, and the first task is to obtain a mathematical model of the system by using ordinary differential equation or ODE, which can be represented as form x dot is equal to ftx in vector form. For a given system t is equal to t naught, we hope the system is defined in near future and there exists a solution to our model. So it is imperative to validate the model and check if there exists a unique solution or not. These conditions are first, the function f should be piecewise continuous in time t, which means it should be continuous in all places except for finite number of points, which is in time t0 to t1. And second, it should satisfy the Lipschitz condition in, in state x, which means if we find function f at x and y, and the difference of the magnitude should be less than equal to constant L times the difference of magnitude of x and y. This gives us the condition to check local existence and uniqueness, which is defined in near future delta time only after initial time t0. If the function satisfies the Lipschitz as stated above, then we can say it is locally Lipschitz at point x. And if the function is Lipschitz on the whole state space Rn, then it is globally Lipschitz. Note that it has to be satisfied with the same Lipschitz constant L in any state space. Now we will formally define stability, and we are using x equal to 0 as our equilibrium point, which may or may not have stability property for all systems. Equilibrium point at origin is defined to be stable if and only if for all positive epsilon value there exists a delta which generally depends upon epsilon such that the norm of initial value is less than delta, then this implies the norm of x will be less than epsilon for all future part. To develop a stronger intuition and understanding of stability, let's visualize it on a 2D plane. For any open ball with radius epsilon, it is always possible to find another ball with radius delta, such that if system starts within this new ball, that is, if the norm of initial state is less than radius of ball delta, then this system states stays within the epsilon ball for all future time. This is the intuition of mathematical definition of stability, that if a system starts close to the equilibrium point, then it should stay close no matter how small epsilon value is. If it is not possible, that is, if there exists a positive epsilon such that it is not possible to find a delta value, that is, the above criteria is not satisfied, then the equilibrium point is unstable. The equilibrium point is asymptotically stable if and only if it is stable and there exists a value r such that as long as initial value of the state is within the open ball of radius r, the system state converges to 0, which implies it converges to equilibrium point at origin. The open ball RA with radius r about the origin and relating it to the example of stability. Here the norm of x is the distance from x to the origin. This ball is a region of attraction of this equilibrium point. The set of region of attraction of equilibrium point means that if the initial state of the system is in this state, then the system state will converge to equilibrium point. If the region of attraction is whole state space, then equilibrium point is globally asymptotically stable, which means it is stable regardless of its initial value. The system will always converge to 0. Global asymptotic stability implies the origin is only equilibrium point. We can also analyze the stability by finding eigenvalue of the system by first linearizing it about x equal to 0 and then checking if the real part of the eigenvalue have negative real part. This method only provides local results and cannot determine if origin is globally, asymptotically, or exponentially stable. Describing more about region of attraction, it is defined as the set of all system states from which system converges to an equilibrium state, like here. It is an index to evaluate stability of the system which leads to safe and efficient operation. If there is a disturbance in the system and the state is still in the ROA, then the system will still converge, like in this example. Therefore, having a larger ROA is better for enhanced transient stability. It is also important to find region of attraction in robotics to avoid its state causing to be uncontrollable or having singularities in some cases. The ROA can be computed using methods like Lyapunov function, sum of squares, sampling-based techniques, and by using learning methods, which we will talk about next. Building up our notion from stability, we define as entity known as Lyapunov function. It is based upon the idea of energy. If the energy is constantly consumed, then the system will eventually converge to an equilibrium point. This forms the basic idea behind Lyapunov stability, to study the energy of the system to find system stability. So we consider this example. This is a 2D example in which has an equilibrium point at origin. The energy of the state is a scalar function and is denoted by the function v in the figure. We draw bounds to all the points in the state space where energy has same constant level, which is C1 here and C2 here. These curves are called as level curves or level surface, and they represent constant energy level of the system. Like for all system states in this example, the energy is constant, and which is equal to S1 in this example and S2 for this example, or C2. Next, we will see how we can use this energy level curve to relate to stability of the system. We consider the system in time invariant form and have origin as an equilibrium point. We study how the energy evolves along system trajectory. If the system trajectory moves towards higher energy level curves, then it corresponds to moving further away from equilibrium point, which suggests the system origin is unstable. To compute the energy in to compute the change in energy along system trajectory, we find the time derivative of the energy function and we obtain the results here by chain rule. It describes how the value of energy function v changes. If this change is positive, then the energy increases along x, like in case 1, and if it is negative, like in case 2, then the energy decreases along system trajectory. This further means the system trajectory intersects the lower and lower energy level until the energy becomes zero, which is at the origin. This indicates system is asymptotically stable, and since we are using concept of Lyapunov, we eliminated the need of solving ODE to find relation of energy. For the case where we observe the energy is constant, we obtain the time derivative of V as 0, which implies the system trajectory moves along one energy level curve. So we won't have convergence in this case. Further, to use Lyapunov function for any general system, we will look into Lyapunov direct method. Lyapunov theory is used to make conclusion about trajectory of system x is equal to fx without finding the trajectory. A typical Lyapunov function has the form v is equal to Rn tending to R, which satisfies the condition on v and v naught and satisfies the system trajectory of the system. This function is called Lyapunov function candidate as of now because we are not sure if it has the necessary properties to serve as generalized energy function. It is Lyapunov function if and only if it is continuously differentiable. So it has continuity that we based our intuition on. V is positive semi-definite. That means if x is 0, then v has to be 0, and when x is non-zero, then d has to be strictly positive. V dot is negative semi-definite, which means if x is 0, then derivative of v should be 0, and smaller than equal to 0 everywhere else in domain D. This is important as it emphasizes the energy function decreases along system trajectory. To apply Lyapunov direct method, we choose a Lyapunov candidate. Then we determine if the function is Lyapunov function for equilibrium point. This is done by validating these above conditions. If the Lyapunov function fails to satisfy any of these above criteria, then we need to find another function v. Side note, if a function is not a Lyapunov function, then it doesn't mean the system is unstable. To understand Lyapunov function, we take the example of inverted pendulum and simulate it in MATLAB. We observe three plots. This is for v, this is for v dot, and this is the phase portrait diagram of inverted pendulum. If we take a closer look at plot of v, then we see it is 0 at origin and it is positive anywhere else. When we take a derivative of v to find v dot, we notice there is no region of negative stability around the origin. At 0 we are fine, but it is positive to the left or right and negative forward and back. The shape resembles like a typical bow, so we are negative along one axis and positive along one axis. We are negative along this axis and we are positive along this axis. And this is the phase portrait diagram of inverted pendulum. To describe about phase portrait diagram, a phase portrait diagram is a geometric representation of system trajectory and stable steady states. The arrow in the diagram are the direction, and if it all converges to origin or equilibrium point, then it is considered to be a stable state. For example, in this example, we see the points are unstable as they are not converging to equilibrium point and they are rather deviating away from origin point, like here. If this example were a stable point, then we would see all the points would converge at the center and we would have a graph something like these trajectory would converge at this point rather than deviating away. Now, let us look into some of the novel works where researchers have used methods to find and maximize region of attraction. We will try to focus on main idea of the paper rather than going into details of it. My colleague will give more intuition about the research paper on the topic Maximum Lyapunov function and domain of attraction for autonomous nonlinear systems.
So we will give you a tutorial on an extensive method how to calculate region of attraction, which is divided into two parts. First, finding a right Lyapunov function, and second is finding maximum value of Lyapunov level set, which is subset of region of attraction. This approach is based on paper Maximal Lyapunov functions and domain of attraction for autonomous nonlinear systems. Let's start with the system model. So your system model is x is equal to f of x, which is represented in the summation of like homogeneous functions fi from I is equal to 1 to I is equal to infinity. So what is exactly homogeneous functions? So it is in functions where all the monomials in the functions have the same degree. Just for an example of a homogeneous function in x and y is f of x and y is equal to x square plus y square is a homogeneous of degree 2, where for example I is equal to 2. Now consider that for your system you have a Lyapunov candidate in a form where numerator is the summation of polynomial function r of I which is function of x, and denominator is 1 plus summation of polynomial functions q of I which is function of x, and n is the number of iterations done, which will be clear what exactly n is in the further slides. And general structure of Ri of x and Qi of x are shown in the bottom two equations in the tab or the slide of the Lyapunov function, where a1 to an plus 1 to b1 to bn minus 1 are the coefficients. For finding all the r of I and q of I required to compute Lyapunov function, we need to calculate all the coefficient of all the r's and all the q's. This can be done by substituting all previously computed r and q and f of I in the equations shown in the top block of the slide, where f of I can be easily computed by decomposing the nonlinear system which you already have and selecting the homogeneous terms of degree I. After substitution, the equation will take form of systems of equations, and by comparing the terms with same degrees, you can get a linear system in form which is shown in the lower block in the slide, where for example you can easily equate a1 plus b1 is equal to 3 and a1 minus b1 is equal to 1. So from which you can easily get a is equal to 2 and b is equal to 1. So giving you an example how to calculate Lyapunov candidate till n is equal to 4. For step 1, n is equal to 2. As f1 is equal to ax is a linear system ax or a homogeneous term of degree 1 in nonlinear system of function f of x, where a has to be a stable matrix with all eigenvalues negative. Same as how calculated for simple quadratic Lyapunov function, we assume Q to be a positive definite square matrix of size of state vector x. Then we substitute this in equation A transpose into P plus P into A is equal to minus Q. As we know A, which is a part of F1 is equal to AX, and Q, we can easily compute P, from which we get R2 is equal to X transpose P into X, which is the exact thing for the quadratic Lyapunov function. And R2 is in form of A1 into x square plus A2 into xy plus A3 into y square. And usually the identity matrix is good choice of Q. As we have computed R2 and Q in step 1, we substitute non-numerical values of R2, Q, F1 and F2 and a symbolic form of R3 and Q1 in a general coefficient form in the equation mentioned in the first block of the slide, which is derived from coefficient solving equation mentioned in previous slides. We get a linear system of equations in form a of n into y is equal to b, where y is a vector of coefficient as mentioned in the center of the block in the slide, which we can solve for computing y. While computing y, the system has many solutions. So to find an optimal solution, we run an optimization problem where we choose the value of y when norm of y is the minimum. Further, for step 3, where n is equal to 4, we substitute all previously known r of I and q of I and f of I in coefficient solving equation and get the linear system by equating the terms of same power. Further, we compute solution for linear system by solving an optimization problem of minimizing the norm of y. Further, this iterative process is carried for n is equal to 5, n is equal to 6, dot dot dot, till we get the norm of y sufficiently smaller so it does not affect the dynamics of equation anymore. After computing all r of I and q of I, we substitute them in the Lyapunov candidate which is mentioned in above slides. And finally, our Lyapunov candidate is computed, which is richer as the function is of higher degree than traditional LQ and quadratic Lyapunov candidate. So moving on to part 2 to find an estimate of region of attraction or to find maximum level of Lyapunov candidate which is inside region of attraction, which can be computed in two ways. Traditionally, as shown in the bottom block of the slide, which is solving optimization problem to find minimum value of Lyapunov function subject to constraint of v dot of x is always 0, which gives you your set C star for which all the states having Lyapunov function value less than that are stable. Second is done by the sampling methods by exploring the states and then deciding what is the optimal value of C star. Out of two methods mentioned above to compute region of attraction, we would be focused or will explain how to compute region of attraction using sampling methods in this paper. But why to study sampling methods? As sampling methods are fast and provide better value of C star, which is a maximum Lyapunov level set, so that might be preferred by some individuals. These algorithms can even run in real time. So that are main two reasons why we are learning sampling methods. But this good computation speed comes with some bad side. That is theoretically there is a possibility that region of attraction might contain unstable states. But all the practical implementation of this algorithm and tested on very large set of trajectories show that your system achieves asymptotic stability in given region of attraction. So let's begin with algorithm 1 of sampling methods. This is a memoryless algorithm. As you already have v of x, which is Lyapunov function computed by the method mentioned in the first paper, so you can easily compute v dot of x. And just take ns, which is number of samples, which is sufficiently large. Starting with algorithm, step 1 is just to set c star to infinity. In step 2 is to run like for loop for n samples or iterate for loop over n samples. In step 3, inside the for loop, there is only one if condition for updating C star, which is entered only when v dot of x is that which is derivative of Lyapunov function is positive or equal to 0 and value of Lyapunov function is less than current estimate of C star. Once you enter the if condition, it updates C star to current Lyapunov value corresponding to the current sample. This if case is shown in statement 4 to 6 in algorithm. Now step 4. Once all the steps are samples are iterated, the last value of C star is your maximum stable level set value. Now let's start with algorithm 2, which is an extension and improvement on algorithm 1. Similar to algorithm 1, you are required to know v of x, v dot of x and number of samples which we get from the Lyapunov function from the paper above. And number of samples is what you select, which is sufficiently large. In step 1, we initialize the lower bound to c is equal to 0 and upper bound of c to infinity. And we also declare an empty array called eta. In step 2, We run for loop for n samples or iterate over n samples. In step 3, inside the for loop, there is first if condition in algorithm line 4, which is entered only if v dot of x is negative and v of x is less than the current upper limit or the upper bound of c. Once you enter the if condition, you add the current Lyapunov value at the state currently being iterated to an array eta. After adding value to eta, we check another nested condition, which is if lower bound of c is less than current value of Lyapunov function, we update the lower bound to that value and program moves to the next sample. In step 4, if algorithm cannot enter if condition statement at algorithm line 4, it checks conditional statement at algorithm line 9. The condition states that if v dot of x is 0 or positive and v of x is less than the upper bound, you enter the loop and update upper bound of c to the current value of the Lyapunov function. And then check if the upper bound is lower than the lower bound, and then we update the lower bound of c as maximum value in array eta, which is less than upper bound. In step 5, after iterating over large sample, we can return the value of c star as lower bound of c, which is the maximum stable level set. These algorithms are self-explanatory and hope so that the tutorial to calculate rich set of Lyapunov functions and its region of attraction will be a great introduction to topic region of attraction.
Now let us look in some of the novel works where researchers have used novel learning method to find and maximize region of attraction. For this, we will look at the paper on safe learning of region of attraction for uncertain nonlinear system with Gaussian processes. As the control starts with designing a model of the system, we aim to minimize error and maximize control law. This tells us which input to apply to the system, and then we can implement this on a real system. However, while doing such modeling and designing the control law, we make some assumptions which aren't true in the real world scenario. Therefore, the solution to this is to introduce some learning methods in control system. Such a learning method would improve model to have better controller as the process of gathering data is optimized and we can achieve high performance results. As the model become exact representation of the real world, the question the paper focuses is it possible to learn system dynamics while guaranteeing stability? The solution to their method is by formulating their problem as a priori model, which is a typical model of the system, and an unknown system model, which is an error term. Now we have to determine a control policy which is safe to use. For this, they start off with a small region of attraction around equilibrium point denoted by S2, which stabilizes the system in a small subspace, and then we can learn the dynamics of our model. As we gather more and more data, we update the estimate of safe set and expand and iterate this process of learning. We eventually explore region and we get the maximum safe set. The Lyapunov stability is used to find solution and give stability certificate to the model. What we want for state space X, we want to have an initial region around an equilibrium point, and we aim to find the larger ROA of the system. For the unknown dynamics, the researcher have used Gaussian process model to learn system dynamics, which basically means we have mean belief over the dynamics, which corresponds to prior model and provides high probability confidence interval. And with more data and iteration, we get good estimate of the system, and we check condition for stability, which eventually results to converging to safe set and finding ROA of the system. Thank you so much for staying till the end and listening to our presentation. Please feel free to discuss or share your thoughts in the comment section.